My dear students, তোমালোকৰ second paper খনৰ that is waves and optics or wave part or আমি already 3টা unit complete কৰিছো। এতিয়া আমি 4th unit to discuss কৰিম। 4th unit to হল velocity of waves। ইয়াৰ content খিনি হল velocity of transverse vibrations of stretched strings, velocity of longitudinal waves in a fluid in a pipe, then Newton's formula for velocity of sound and Laplace's correction. এই ইউনিটটোৰ নোটখিনি অলৰেডি মই তোমালোকক দি দিছোঁ আৰু সেই নোটখিনিৰ পৰাই আমি এতিয়া ডিসকাস কৰিম। সো প্ৰথমতে আমি ডিসকাস কৰিম velocity of transverse vibrations of stretched string. Firstly, let us consider a very long string stretched by tension between two fixed points at x equal to 0 and x equal to L. So here we need to consider an approximation, that is length is very long with respect to radius of the string. So the string is fixed at the ends, that is at x equal to 0 and x equal to L. Now if we plug the string at any point and then release, we will observe transverse vibration of the string, and that vibration will proceed, will travel through the string, and depending upon the point where we have plugged, we will obtain different mode of vibrations. So if we plug here, then we will obtain fundamental mode of vibration and the string will vibrate like this. Similarly, if we plug at x equal to 0, sorry, x equal to L by 4 or x equal to 3L by 4, then we will obtain this mode of vibration. Similarly, if we plug at x equal to L by 6 or 5L by 6, then we will obtain the third harmonic and the string will vibrate in this way and then reflect back. So our aim is to determine the speed of the transverse wave generated in the string. So to do so, firstly we need to consider a pulse of the string, any one pulse, say this one or this one, any arbitrary pulse we have to consider. So the string is long, দীঘলীয়া এইফালে, ইয়াৰে যিকোনো এটা অংশ আমি লৈ লৈছোঁ আৰু ডিউৰিং ভাইব্ৰেশ্যন এইটো পালছ জেনেৰেট হৈছে এই অংশটোত। এই ফিগাৰটোত আমি দুইটা পজিশনে দেখুওৱা হৈছে ষ্ট্ৰিংডালৰ। undisturbed position, this is the undisturbed position, and this is disturbed or displaced position or vibrational position. So আমি প্ৰথমতে ষ্ট্ৰিংডালৰ এটা সৰু অংশ এলিমেণ্টেল length এটা লৈছোঁ of length del x between x equal to x1 and x equal to x2, and at equilibrium the tension force acting at the two ends of the elemental length is equal and opposite. But when the string is displaced, that is during vibration, the tension force acting at the two ends of the elemental length of the string will be like this. Here we have resolved the force, tension force along the string in two different components, that is horizontal and perpendicular, horizontal and perpendicular at both the ends. The total x and y directional force on the elemental length will be t cos theta 2 minus t cos theta 1 along x direction and t sin theta 2 minus t sin theta 1 along y direction. You see here. So, t cos theta 2 along positive x direction and t cos theta 1 along negative x direction. So, total x directional force is t cos theta 2 minus t cos theta 1. Similarly, t sin theta 2, this should be 2, শুদ্ধ কৰি লবা এইটো, sin theta 2 along positive y direction and t sin theta 1 is in the negative x direction. So, total force along y direction is t sin theta 1 minus, sorry, t sin theta 2 minus t sin theta 1. Now, if we consider an approximation that the transverse displacement is very, very small, that is amplitude of the vibration is very, very small. So, you consider a vibration of very small displacement, then what will happen? This theta 2 and theta 1 will be very, very small, and for small angle we may approximate cos theta 1, cos theta 2 to be equal to 1 and sin theta 1 and sin theta 2 to be theta 1 and theta 2 respectively, which may be further approximated as tan theta 1 and tan theta 2. So, considering this approximation in equation 1 and 2, here we obtain the net x directional force to be equal to 0 and Fy equal to t tan theta 2 minus tan theta 1. Here what we observe that net x directional force vanishes. So, the elemental length is under y directional force, and under this force that element will vibrate in a direction perpendicular to the length of the string or perpendicular to x direction, that is along y direction. Again, tan theta is represents the slope of a curve at a particular point. So, tan theta 2 represents the slope of this curve, of this pulse at x equal to x2, and tan theta 1 will represent the slope of the curve at x equal to x1. So, we know the slope is written like del y del x. So, tan theta 2 will be del y del x at x equal to x2 and tan theta 1 will be del y del x at x equal to x1. And now, if we represent del y del x in terms of a function f(x), then del y del x at x equal to x2 will be f(x2), and similarly del y del x at x equal to x1 equal to f(x1). So, total y directional force is equal to t f(x2) minus f(x1). The value of the function f(x) at x equal to x2 or slope at x equal to x2 may be obtained using Taylor series. So, since x2 may be written in terms of x1 plus delta x, so this function may be expanded using Taylor series around x1 like this. So, here we obtain some terms containing delta x of different order. Here delta x to the power 0, delta x to the power 1, delta x square, then we will obtain delta x cube, then another term containing delta x to the power 4, like this. Now, if we assume that delta x is very small, then the terms containing delta x square and higher order terms may be neglected, because delta x square, delta x cube, delta x to the power 4 will be smaller and smaller. So, neglecting all these terms, we can write f(x2) equal to f(x1) plus delta x del f del x at x equal to x1. So, f(x2) minus f(x1) equal to delta x del f del x at x equal to x1, and this can be generalized like this: delta x del del x, so f is del y del x, so f(x2) minus f(x1) is delta x del 2y del x square. So, total force is y directional force is Fy equal to T delta x del 2y del x square. Now, we will use Newton's second law, which is what? The net force on the mass element is equal to the mass times the acceleration. So, total force is equal to mass into acceleration. Here mu is the mass per unit length of the string and delta x is the length of the element. So, mass of the elemental length is mu del x and del 2y del t square is the acceleration of the elemental length of the string. So, F equal to ma. So, rearranging this equation, we obtain del 2y del t square equal to mu will be here. So, T by mu del 2y del x square. So, if we compare this equation with the standard differential equation of wave motion, then we observe that v square equal to T by mu. Here v represents the velocity of the wave. So, velocity is equal to root over T by mu. So, this is the velocity expression that we need to determine for the transverse wave in a straight string. Here the velocity depends upon the tension under which the string is stretched and the mass per unit length or linear mass density of the string. So, this is the expression for velocity of the transverse wave in a straight string. Thank you.